Okay, part 2 for week 7 is going to be a rapid run through earthquakes and volcanoes. So we talked about plate tectonics and moving the lithosphere, and so those tectonic movements can result in kind of two general types of reactions. One is folding and the other is faulting. When strain or stress is put on some kind of landform, rock, mountain, land surface, there can either be result in intentional stress, so pulling it apart, where you have divergent plates, or compressional stress, pushing it together, or there can even be twisting or transforming stress. The stress causes strain, and the strain is how the rock or the land surface responds, and it will respond by folding if it's plastic or not very brittle, or if it's over a slow amount of time, it could fold. It also responds by breaking. So let's look at folded landscapes first. Okay, so typically folding happens through compression of converging plates, relatively slow, and you get these landforms called parallel mountain landforms. This would be really common in West Virginia, where you get these kind of ridges that just parallel each other, and these valleys, these little mountains and valleys, called synclines and anticlines. On a larger scale, like a continental scale, you would have large domes or basins. But if you're looking at just a small mountain ridge scale, as these two plates converge together, the landform thickens in between. It pushes some of the land up and drops some of the land down. So the anticline is kind of the hill, the syncline is the dip, and thanks to the stratigraphy we can see that. And you can also see it in the real world. So this is outside of Barstow, and you can see those different layers of rock and how they create that zigzag pattern. Here's a little closer, very heavily compressed lands. That just think about these as sea, ocean sediments laying down very flat at one point in time, and how they've been moved and folded. Faulting is the stress that happens that causes a fracture. If it's too rigid or it happens too fast, and this results in an earthquake. So that sudden fracture of the ground. When an earthquake happens, the point that the earthquake, the first break or the point of break, is called the focus. The epicenter is the place on the surface of the earth directly above the focus. And so when we talk about earthquake damage, they often will give you where the epicenter was or where the focus was. And so you can imagine if the focus were not very deep, that the earthquake could have a lot more impact. Sometimes you can have big earthquakes, but the focus is so deep into the earth that we don't even notice it on the surface. The rupture or the crack that happens from an earthquake is called the fault. So earthquakes have two major movements. One is called the P wave, or the primary wave, or the compression wave. I think the reading has it called as the compression wave. And this is just the back and forth compressed in and out motion of the earth. The secondary wave, or the S wave, or the shear wave, is the back and forth shaking motion. And it's the shear wave that causes the most damage in an earthquake. And so here's some examples of a shear wave. I think this is the Loma Prieta earthquake in California, and a result of unsteady sediments and soil. So when we look at earthquakes, not only is the shaking and the jolting and the fracturing a problem, but there is a secondary problem that can happen called liquefaction. Some people say liquefaction. So if you have sediment that is near water, or filled land that's near water, when you have the shaking of the ground, it pushes the water up between the sediments, pushing those sediments apart and almost creating a fluid or just a big muddy liquid. And this can remove any of the solid ground or the substance that people are standing on or buildings are standing on. And that accentuates the damage in an earthquake. So here's kind of an example of soil being pushed up because it was suspended or liquefied. Here's an example of some apartments in Japan that were on soft sediment or fill sediment, and as a result of ground shaking, they just lost their footing and tipped. It's kind of a frightening image. This is of the San Francisco Bay Area, and the red area is areas that are filled, kind of when we took back some of the ocean land for buildable land, filled it in with gravel and rock and other sediments. It's not solid rock, and so this is going to liquefy very easily. And kind of this is an example of the number of buildings that are in that area. Another impact from earthquakes is a tsunami. Tsunami is an ocean wave created by kind of uplift of the ground underneath. If you have a break under the water and the ground is uplifted, that displaced water begins to move out in all directions. And in deep water, vessels don't even notice sometimes that they're going over tsunami deposit, but it's very dangerous when it gets up onto shallow land or up onto land and comes onto the shore. So here is an example of the damage from a tsunami, and this was from a tsunami that happened across the ocean, and this was the amount of energy that was still available to that wave when it crossed the Pacific. Now in Oregon we have a potentially very hazardous situation. We have a subduction zone, so the Juan de Fuca plate has upwelling, and there's a divergence here at this ridge line, but this angle of the plate is moving toward the Pacific or the North America plate, and the North America plate is moving toward that edge of the Juan de Fuca plate, and so that heavy sediment is diving down under the coast. And historic records show that about every 500 years or so there is a giant catastrophic earthquake along the Oregon-Washington coast, so we are, I think the next prediction is about within plus or minus 50 years, well not minus 50 years or we would have had it. So within the next 50 years predicted to be the next large earthquake. Now if you have an earthquake across the Pacific, you have several hours, even though they can travel at ridiculously high speeds, you have several hours to get people off the coastline and get people to safety. If you have a subduction zone quake of large magnitude that is not a deep focus, then in Oregon you have maybe 20 minutes to get to safety, and these waves can travel inland very far. So there's not a lot of time with the Oregon situation, Oregon-Washington situation, to get to safety. So one of the things to do when you go to the coast is really kind of watch those tsunami warnings, the evacuation lines, know where to go, know how much time you have. I included in the reading a video of the tsunami from the 2011 Japanese earthquake, and it's really disturbing. So kind of watch it and be prepared to be moved. It starts out kind of lighthearted as young people are kind of feel an earthquake and watching the water change, and then it gets very silent as they see the devastation. And you'll notice that in a very short amount of time, it turns from kind of an interesting thing to a roaring wall of water. The second kind of earthquake type that we're going to talk about in this book is a transform fault. So this is two plate boundaries moving side by side. There's not a lot of uplift or downdropping, but potentially very large quakes. The next one I think predicted is I think to be able to make a break of about 300 miles along the along the California landscape and be of a magnitude of about 8.1. One of the things with, so here is the rift created, I think this is the African rift, I do believe. Shoot, I'm not sure where that is. I lost my label. So just ignore that. So one of the things you see with transform faults is offsetting. So kind of that shaking. So here's agricultural fields that had been straight and were pushed kind of sideways by that S wave. Here is an offsetting of a road by probably 7 inches or so ground movement. So there's a couple ways that we describe earthquake intensity. One is the Richter scale, and the Richter scale is a logarithmic scale, so that 2 is not just twice as big as 1 and 4 is not twice as big as 2, but it's a magnitude of difference. And where was I had an example. So we're looking, what's really interesting is they're not even talking about level 9 magnitudes, and this is what we're thinking in Oregon along the coast as these much higher magnitude earthquakes. So that's the largest earthquake recorded in 1960, and the devastation was huge. The other scale that's used is called the modified Mercalli scale, and this is a scale that describes not the magnitude, which is the amplitude of the earthquake wave, but this describes the amount of damage that's seen. And so you could have a lot of damage, but the magnitude wasn't that large. Okay, so volcanism. So it's interesting how these two are correlated all along plate boundaries. We have movement along the plate boundaries that causes earthquakes. We have upwelling of magma along these plate boundaries that cause volcanic eruptions. We can classify volcanoes into 2 types, explosive and effusive. Effusive volcanoes are common when you have divergent plates or hot spots. They have a lot of lava. They tend to be just lots of volumes of lava. They make really huge landforms. They tend to be more gentle. You don't have to. They're not a Pompeii kind of episode. The magma or the lava coming from the volcano is very low viscosity, which means it's kind of like Hershey's syrup. It's very thin. Once you start pouring it, it just kind of runs and runs. And these are responsible for the volcanics in Hawaii and the big volcanic plateaus in Oregon called the Columbia River basalts. The other type is an explosive volcano. This is very common with subduction zones. So what we have this subduction zone off the coast of Oregon, and that's created the Cascade Range, which is Mount St. Helens, Mount Hood, the Three Sisters. All of those are explosive type volcanoes. A lot of pressure builds up because the magma is very sticky. It's very thick. It's probably more like hot fudge. And these create cinder cones and composite volcanoes and pyroclastic flows. I don't know why that's there. It's just kind of cute. When we look at lava on the surface, there's a couple types that we talk about. One is which is, you can see that's a stickier lava. It tends to be much more angular. It flows slowly, breaks up. And Pahoehoe lava, which is more runny and ropey. Lava can form cinder cones. Cinder cones are explosive volcanoes. They tend to be very conical. They have their cone in the top, a little crater. Very little lava flow, but large amounts of pyroclastics, which means things that are thrown into the air. Pyrotechnics is fireworks. And so these are rocks that are in the air and they're hot. So hot ash, hot scoria, little bits of lava with lots of holes in it, and small like lava bombs. And in Oregon, we see those in Black Butte or Lava Butte. Here's an example of scoria. It's just a lot of gas bubbles, a lot of holes in that lava when it's thrown up into the air. Here's an example of a cinder cone. If you were to dig into this, and road crews do a lot because they get road gravels from cinder cones. Here's another example of cinder cones. Composite or stratovolcanoes are also explosive. They're conical shape. They have a much more developed crater. And they have pyroclastic material too, but they also interlace that with or interlayer that with lava flows. So you have very explosive andesitic magma, lots of ash, lots of lava, as I said. So you see that with Mount St. Helens, Mount Fuji, Mount Hood, Places. Is that right? Yeah. Have it in common. They're all on the edge of the ring of fire. So here would be kind of a cutaway. And again, you can put the law of superposition in effect here when you look at the just different flow levels. It's a nice kind of just a classic. This is the one when you drew a volcano in 3rd grade. This is what you drew, Mount Fuji. An example of effusive volcanoes is a shield volcano. And a shield volcano has very little ash, or very little cinders, tends to be basaltic lava. It's very thin, it flows very hot, and it builds these really broad, low, shield-shaped features. So Mauna Loa in Hawaii is probably considered the largest mountain on Earth. And if you I think I have an example of that. If you put Mount Rainier beside Mauna Loa, Mauna Loa is way bigger. But only a part of it sticks out of the ocean. And so here's kind of that low relief with Mauna Loa. One thing I'm just backing up with explosive volcanoes, sometimes they can create what's called a caldera, and this is where a huge amount of material is exploded off the top of a volcano, leaving kind of this wide, thick crater. And this is what created Crater Lake in Oregon. Here's an example of what was once historic Mount Mazama, and that, I don't know, is it like 5,000 feet of rock blew off Mount Mazama to create Crater Lake. Sometimes you get these lovely vents and cores, volcanic throats that have cooled, and then the land around have been eroded. They make amazing landscapes. Here's an example of the flood basalts, the Columbia River basalts that just over time built up layer and layer and layer of these basalt deposits, and then later have been eroded by exogenic processes. A lahar is a superheated mud flow, and in 1985, with the Ruiz volcano, killed 23,000 people from this mud flow. We had some of that with Mount St. Helens too. The ice melted, kind of a flash melt, picks up hot ash, hot mud, and then just moves it down the mountainside at just phenomenally fast paces. Here's an example of pyroclastics. Just imagine ash, cinders, scoria, and large hunks of rock being thrown out of the throat of the volcano and then just landing on the landscape. A superheated ash cloud can also occur with explosive volcanoes, and this is the event that killed the people in Pompeii from Mount Etna when that exploded. This just huge ash cloud moved it. I think readings said almost 200 miles an hour and covered hundreds of miles of land. So, you're not going to fight that kind of volcano. There's not much you can do. You can just hope you're not living on the flanks of that volcano, but probably you are because volcanic landscapes are very fertile. But I think this is from the Shield volcano in Hawaii, and because this magma flows rather slowly, or the lava flows very slowly, people try to contain it. So there are instances where people have built dams of earth with earth movers, where they're trying to cool that leading edge of the lava in order to slow it down. Here's the truck, or the bulldozer, trying to kind of change the flow of the volcanic activity. And then usually, though, I think nature's going to win this one. So that's an overview. There's a lot more detail in the reading, but I think this should give you a really good start with the study guide and help you with the quiz.